going to talk about two concepts that are brand new to you that we did not discuss last year. We're going to discuss drag forces and how to calculate the drag force on something. And then we're also going to talk about objects that are traveling around banked curves. So let's do the drag forces first. So we all know that as something falls or travels through the air, it's going to encounter a drag force. So if you are, for example, in a parachute, gravity will pull you down and the drag force will act against you to slow you down. If you're in a car, of course, you have the acceleration of the car engine taking you forward, and then the drag force is resisting that forward force from the engine, and it will affect your acceleration a little bit. So in both instances, drag force is a form of friction. But unlike friction, the drag force will change depending on the object's velocity. So the faster you're going, the more drag force you have, whether you're traveling downward or across. So this is applied, and then this is FD. Sometimes you'll see the drag force labeled as capital F, little d. Sometimes you'll just see the formula for it written next to the vector, which is about what I'm about to show you. So I prefer to do it like this, or sometimes I'll just do a capital D for drag force. Okay, so what happens is that eventually you get going so fast and the drag force gets so large that the object reaches what's called terminal velocity. And the terminal velocity is the fastest the object can travel. It won't accelerate anymore. So when you jump out of a plane, you eventually reach that point of terminal velocity where your downward weight equals the drag force that's pushing you up. So drag force is typically a formula. Well, it is a formula. It's not typically a formula. It is. But it follows this generic template for a formula. B is a constant that depends on the shape of the object that's falling. And velocity is V is of course your velocity. And N is an exponent that is approximately 1 whenever you're going at low speeds and 2 at high speeds. So the faster you go, the larger your drag force becomes. So if we had to draw a free body diagram for what's happening, we would have our weight and then we would have our drag force acting in the opposite direction. So if we're looking at some point along this object's fall, its net force, or the sum of all its forces, would be the weight of the object minus your drag force. When it reaches terminal speed, then that means you don't have any more acceleration. So these two forces are equal and opposite to each other at terminal velocity. So the larger this is, so let's rearrange this. So let's rearrange this formula to solve for V. So we get mg over b equals v to the n. And then we're going to take the inverse power of n from both sides. And we end up with a terminal velocity formula that looks like this. So the bigger your b value, the lower the terminal speed. Right? Bigger b, lower terminal velocity. So remember that b is a constant that depends on the shape. So this is why parachutes are so large, right? Because we are trying to maximize that surface area. We're trying to maximize this b value. which will make your terminal velocity very low. And then with cars, it's the other way around. Cars work to have a small b, because the smaller the b value, the higher your terminal velocity can be. So race cars can go faster. There is a little bit of calculus that can go along with this. I've seen this done with a few FRQs. We're going to do some practice later this week with how to put calculus on top of all of this. So let's talk about banked curves real quick. So first of all, what is a banked curve? So typically when an object or a car, we're going to stick with cars because they're the things that are going to go on a banked curve. And this is like from the top, though. So when a car goes around in a circle, we've only been really talking about flat horizontal circles. So he's making the curve. It's the friction, right, between his tires and the road that is providing your centripetal force. If that friction was not there, that car would spin out of the curve and it would not be able to stay in this rounded position. So we've talked about that last year a little bit. I believe I mentioned it in the last video. I might have, I can't remember. So banked curves are curves that come up at an angle. So now I'm going to draw it not from the top-down picture, but like from the front view. So this is a car from the front view. So banked curves are very common in like racetracks. It's when the car goes up onto the curve and then comes back down. So let's draw a free body diagram to kind of show us what's happening with our banked curve, because it's a pretty unique situation. So we still have gravity acting downward, and we still have the normal force acting upward. But banked curves are typically frictionless, or banked curves are this angle, rather, that the curve banks at. It's not frictionless, but it's chosen in a way so that the car can make the curve without friction. So this means that you'll probably go faster. So if that's the case, if there's no friction pulling the car this way towards the center of the circle, then what's providing our centripetal force? And what's providing our centripetal force is going to actually be the horizontal component of your normal force. So if this is an angle here, and this is your normal, right, and this is your gravity, it's this part of your normal force that is keeping the car going in a circle. So in this case, it is going to be your sine. And this is also going to be your net force. So this is the part that creates this lovely thing here. So I know you guys are typically used to dividing up your gravity vector, but when you deal with banked curves, that's not what you do. You want to look at what's happening between the car and the road, and that is your normal force. So the vertical then, Fn cosine theta, will balance out with your weight of your car. So if you wanted to find the angle that the car or that the banked curve would need to be at to make a particular turn, let's say, you can say Fn equals mg cosine theta. And then you can substitute this in here. So we've got mg over cosine theta times sine theta equals mv squared over r. And then that equals mg tangent theta equals mv squared over r. The m's cancel out. and then you end up with this expression, tangent theta equals v squared over gr, because I just divided both sides by g. So you can see that the angle of the banked curve doesn't really depend on the weight of the car at all. So the m's end up canceling out. The mass is inconsequential. The only thing that matters is how fast the car is going and the radius that it's trying to make. And then that will help you determine the angle that the bank needs to be at in order for the car to take it safely. Okay, that's all I wanted to talk to you guys about with this video, and we will do some practice with both of these concepts when you get back.